Bear with me. I'm going to copy. I'm going to come here. I'm going to paste. Okay, and then I'm going to make it small. Right. So we need to know that distance y. Okay, so if we look at the distance y is basically d divided by 2. Okay, it's basically d divided by 2. So the material we're going to use, or the structure we're going to use, is this one. I'm going to highlight is 41.7. Okay. So we know D is what? 205, right? D divided by 2, so 205. So the moment will be equal to plus the direction is the same. 100 times 10 to the power 3 multiplied by D, the value for this 205 in millimeters. In meters is 0.205 divided by 2. So from here, we get 25 to the power 3 times by 0.5 plus by 100 power 3 times by 0.205 divided by 2. So it's 22.75 times 10 to the power 3 Newton. Is it Newton meter? Yep, Newton meter. Okay, it's 22.75. Okay, so for this case, we again also need to check. So we are going to not check. I'm sorry, it's not check. It's not the right word. So the formula we're going to use is stress Z is equal to mz over I not Z mx over Ixx multiplied by y. And as you can see, element A is going to be tensile. We're going to have positive, or I'll put the word tensile. And for element B, the value will be equal to what? 0, because it's exactly at the what? At the centroid. Okay, so we know all this now. So another thing over here is we will have our Vy is equal to 25 times 10 to the power 3 Newton. Okay, we have a Vy. So from the Vy over here, how is it going to affect element A and element B? So we draw this view again. Right, we draw this view again. Right, and this is our element A. Over here is our element B. So we do our, before I do that, you will be asking why am I doing that? We know that we have a load coming down this way, and this load is 25 times 10 to the power 3. Right? So if we were to design the shear flow, it's a white flange. Now you realize that something changed. The shear flow will not be equal to 0 now. Okay, at point B. Right. So when we apply the shear, right, shear stress, this will be equal to By over Ixx Qx over T. And what we realize now, right? What we realize now. So let me put in the transformation that this is our x, and this is our Y. We have rotation about Z. Right? So what we realize over here is the shear stress at element A and element B will not be equal to 0. Okay. On the previous one, on shear, right, element B, right, the shear, as we have highlighted earlier, right, the shear for element B is equal to 0 due to the Bx. Okay, By will not be equal to 0. Okay, and you will know why, because of the what? Design of the shear flow. Okay. So let's count. I'm going to calculate element A and element B for the shear first. Okay. So let's focus on element A. Okay, let's focus on element A. Okay, let's focus on element A. And the good thing is we no need to calculate our second moment of area. It is more or less like even. Okay. Right. So we are now going to deal with this one first. Okay. We are going to deal with Vx first. So we know that we have Vx, and Vx, when we formulate, is equal to 16 times 10 to the power 3. And we know that the shear flow is doing this. So we have our element A, and this is our element B. Okay. So let's focus on element A first. Okay, as I was saying. So for element A, so we know that the formula we're going to use is shear. So if I were to draw our transformation, right? Well, wait, our transformation, I have to be sure. Yeah, this is X, this is Y. We are going to find the shear in the ZX direction. So this is equal to Vx over Iyy Qy over T. Okay. So we know that Vx is equal to 16 times 10 to the power 3. And we also know that our Iyy from the table, Iyy is 9.01. Right? Thickness T. So this is the thickness that we are looking for. Right? So that's the thickness. So if we look at the thickness over there, the thickness is the thickness of the flange. So thickness of the flange is 11.8 times 10 to the power minus 3 meters. We are going to use wide flange analysis. So wide flange analysis, this is the area to consider, right? Because this is a terminal. This is a terminal. The terminal at the top and the bottom are not related. So it's a wide flange. Okay, so we are going to look at element A. And we are given that element A, the distance from here to here, right, is equal to what? 75 millimeters. That's given to us. Okay. So we are going to find so our y axis. Let me put out our axis. Okay. So we know that this is our y. So we're going to take first moment of area about y axis. So when there's an axis of interest, this is our width. Over here, this is our depth. Okay. So from here, qy will be equal. So the width is equal to our thickness of the flange is equal to 11.8. The depth we know is 75 because it's given to us. The distance from the edge to point A. And then the y bar. So the y bar is equal to what? So it's equal to BF, right? So BF we know is 166 divided by 2, right? 166. So BF you can see is this is BF, okay? So 166 divided by 2 minus, okay, minus by 75 divided by 2. So why is that? Okay. So I want to know our, I have to write out the formula first. I don't want you all to be confused. My apologies. So we know that IYY is equal to width times depth multiplied by Z bar. Okay. Oh, sorry, for this case, X bar. Because it's Y X axis. Okay. So, yep. So we're correct is 9.01. So we know that we know that 166 divided. So we want to know. So we want to know what is the distance we want to know. We want to know this distance. Okay, the distance from here to here. So this is our X bar, right? So to get that distance, we know from here to here, this is equal to 75 divided by 2. And the distance from here to here, right, is equal to 166 divided by 2. So we can find our X bar, okay? So with that, is you get 166 divided by 2 minus 75 divided by 2 times by 75 times by 11.8 is equal to 40.268 times 10 to the power 3 millimeter cube. So this is equal to 40.268 times 10 to the power minus 6 meter cube. So that is for the force, the shear force in the X direction. Okay. Okay. So once we have that, the next thing we are going to do, as I said, we are still focusing on element A. Okay, so I'm going to sketch out the same cross section. So now we are going to look at shear ZX, which is now equal to Vy over Ixx Qx divided by T. Okay. So we know that we have our Vy, and our Vy now is coming in this direction. And we know the Vy magnitude, which we have calculated or analyzed, we're breaking this down. This is equal to 25 times 10 to the power 3. Okay. So now we were to draw the shear flow. Okay, now we sketch the shear flow this year. So over here, this is our element A. All right. So we know that we have a Vy. Okay, we know that we have a Vy. Verify times 10 to the power 3 Newton. And we have to know what is our Ixx. Okay. So Ixx, you go to the table, we get 40.9. Right. And then next we need to know our thickness. So the thickness is still the same thickness as TF, right? So it's 11.8 because this is the thickness that we're going to take, right? So this is still 11.8. The only thing that we need to find out now is our first moment of area, Qx, is equal to width, depth, y bar. Okay. So the axis of interest, this is our x-axis, right? So when that's the case, this will be our width, and this will be our what? Our depth. Okay. So the width up to this point, right? So the width is equal to the width is equal to 75. The depth, which is T, okay, the depth, which is equal to TF, and TF is 11.8.